All right. Hello, everyone. This is my first attempt at a lecture using my iPad, so let's see how this goes. I want to start out with a recap from the last lecture. You'll recall that we are talking about conductors and Ohm's law, and we started out with the relationship that J, the current density, is proportional to F, the force per unit charge, which I would also call the field, applied, and they're connected to each other via a proportionality constant, which is the conductivity, and that's the reciprocal of the resistivity, which is a quantity you might be more familiar with. So basically, this is a very simple equation. It just says that the current density is proportional to the force per unit charge with the proportionality constant of the conductivity. Now, this expression is what I would call a local formulation of Ohm's law. And what I mean by that is that it tells us a story. If you have a bulk conductor in some sort of complicated vector field with, vectors pointing in all sorts of directions, what this principle tells us is what's going on in this small neighborhood that is in the some portion of the bulk. So that tells us the relationship between the field and conductivity essentially in the neighborhood of this blue dashed point right here. Okay. Now, as we'll see, V equals IR, that expression, which you're more familiar with as a version of Ohm's law, that expression is a macroscopic formulation, and it comes from essentially integrating all of the points in this bulk, summing over all of them. Okay. And that formula, especially the R part, depends highly on the particular geometry of the problem. So, how we learn out the specific formulation of Ohm's law depends on macroscopic properties. In other words, what is the geometry? Are we dealing with a wire or a sphere? What are the symmetries? Things like that. But the J equals sigma F formulation essentially tells us something that is generally true for any given point. If I know the conductivity at that point and I know the field at that point, then I can determine the current density. Now, I mentioned this in the lecture, but it bears repeating, mostly because it gives you, I would say, a sense or an understanding of how tensors work. This is good for sort of flexing your mathematical muscles. Generally speaking, the conductivity of a material could be position dependent. It could be a non-uniform material. And so we would think of sigma as being a function of R, meaning that you have a different conductivity value at different positions. I would describe, or one would describe this sort of conductivity or this sort of material, rather, as an inhomogeneous material. But it's even further than that. You can have special materials that are designed that they have different conductivities in different directions, and you would call that anisotropic. And in that case, you have to actually represent the conductivity as a tensor, an object that has two indices, I and j. And the way to think about conductivity as a tensor is it tells you the conductivity of the material in a particular direction, I, due to the field in a particular direction, j. And we can represent this using a matrix in the following way. Basically, to first order, the way you might think of this is the diagonal elements are the ones that make the most sense. That I might have a different, if I apply a field in the x direction, I might have a different conductivity in the x direction. If I apply a field in the y direction, I might have a different conductivity in the y direction. And if I apply a field in the z direction, I might have a different conductivity in the z direction. But it is possible to have situations where you have these cross-diagonal elements, or off-diagonal elements rather, where for a given field applied in one direction, the conductivity seen by the charges in a different direction is different. And so you could have this very, very complicated matrix, and we I'm just introducing this to sort of give you a sense of how these things can be formulated, but generally in this class and in a lot of contexts, in most ordinary contexts, we're going to assume that the conductivity of the bulk is homogeneous, meaning that it's constant at all points r. So for any point r, it's just a constant value, sigma sub 0, sigma naught, and that it's the same in all directions, which is isotropic, which we can represent by saying that this tensor, sigma ij, is equal to a constant times the Kronecker delta. And the definition of the Kronecker delta is that the value is 1 wherever I equals j, and it is 0 everywhere else. And that would give you this matrix here where all the off-diagonal elements are 0. And furthermore, all of the on-diagonal elements are the same value, sigma naught. Now, in the case of an isotropic and homogeneous conductor, then it is also true that the direction of the current density is parallel to the direction of the field applied. So these assumptions make life a lot simpler when they're true, but it bears repeating that in cases of extremely high field strengths, that this assumption may break down. Again, conductivity is an intrinsic property of the material, but also the conditions that that material is under, conditions like the temperature and the pressure. And we can also define a quantity called the resistivity, which is, again, the sort of inverse of the conductivity. It's how much current flow is obstructed. And you can write that as the inversion of the conductivity tensor. But in the case where you can represent the conductivity as a scalar value, i.e. homogeneous and isotropic, then it's easy enough to just say that the resistivity is 1 over the conductivity. Okay. Now, for materials, we can sort of classify them. A perfect conductor would be one in which the conductivity is infinite, the resistivity is 0. An insulator is one where the conductivity approaches 0 and the resistivity approaches infinity. And in the in-between zone are real conductors, or you could call them poor conductors, where the conductivity has some finite value between 0 and infinity. It's important to point out that there is no hard line here. It's a gray boundary between all of these things. It's a spectrum. And as I went over in class, different materials can span wide magnitudes, everywhere from 10 to the minus 8 to 10 to the 24 when it comes to resistivity. So an example of two conductors would be silver and graphite, which have resistivities of 1.59 times 10 to the minus 8 and 1.6 times 10 to the minus 5 ohm meters. Examples of semiconductors would be seawater and diamond, which respectively have 2 times 10 to the minus 1 and 2.7 times 10 to the 0 ohm meters. And examples of insulators would be glass and Teflon. And these are things that, depending on the specific type of glass and Teflon, can have some ranges. So glass can vary anywhere from 10 to the 9th to 10 to the 14th ohm meters, depending on the specific glass. And Teflon similarly ranges between 10 to the 22 and 10 to the 24 ohm meters. Now, in the formulation that I showed above, this one right here, oops, I used the eraser somehow. How did I do that? In this formulation, I was using this general letter, F, which represented the electromagnetic field, which is force per unit charge. And that general concept has both a contribution from the E and B fields. You can write it, and this is something that should be familiar to you from the first semester, as E plus V cross B, where if I just multiply this by Q, it gives me both the magnitude and direction of the electromagnetic force. But it bears saying that in most cases, the contribution from V cross B is going to be negligible. Specifically, in cases where V, the velocity of the typical velocity of the electrons of the charges, if it's much smaller than C, then you can probably neglect, or you can't probably, you can generally neglect this term or approximate F as just being E. No, there are exceptions, as I mentioned, plasmas, if you shoot a really high intensity laser at a local spot. And of course, in the universe, there are lots of extreme examples of things that will break this. Large cosmological stuff, supernovas, stars, who knows. You can always come up with extremes in our universe. But if you're dealing with, wires, stuff that's sort of ordinary terrestrial, most of the time, unless you're doing, really out there experiments, which lots of people do, but ordinarily you can make the approximation that F is approximately E, and so that approximation looks like this: J equals sigma F, which is approximately sigma E. And Ohm's law in this form is therefore not a true, always correct formulation, but rather an approximation. And it's really just the first order term in what is a longer power series that has higher order corrections that, again, become more important under more extreme circumstances. Um, there's a way to give a hand wavy argument for why the V cross B term is negligible. And the way to do it is you go back to what you did first semester and you calculate the B field in terms of the current density. And you can rewrite mu over 4 pi naught as being 1 over 4 pi E naught times 1 over C squared. Later in this course, you're going to learn why that relationship is the way it is. It's pretty deep and really interesting. But for now, we can just take that for granted. And if we look at a particularly simple case where the current density is equal to the charge density times a velocity, we can rewrite J as being rho V. And we can take the magnitude of V out of this integral and just use V hat here. And if we write the formula for E, we get basically a formula of the same form, except that it's missing this term. In other words, B is approximately equal to V over C squared times E. And from this, you can see that as long as V is much, much smaller than C, B is negligible compared to E. And that's just kind of a way of seeing why we can approximate sigma F as being sigma E under most ordinary circumstances. So now we're going to talk a little bit about steady currents. This was what we got to towards the end of the last lecture. A steady current is one where the current has no divergence, or I should say current density, where the current density has no divergence. And so if you take the divergence of J, you get 0. We talked pretty exhaustively in the last lecture about the continuity equation, and I will point out to you that this form of continuity equation is extremely important, and it comes up in different ways in different contexts with different variables throughout this course. So it really is good to understand it. And we talked about how if you have sort of a non-diverging flow of charges that pass through a volume, the same amount of charge will enter the volume as exit the volume, and therefore the total quantity of charge or the total density of charge will remain constant. So if del dot J equals 0, then d rho dt equals 0, and that means that the charge density is constant. If you did have a diverging current density, then that would mean that basically more charges are leaving that point in space than entering it, and so by definition that or the other way around, I should say. So either by definition charge is building up in the volume, or charge is leaving the volume, more is leaving than coming in which case d rho dt would not be 0. It would either be positive or negative, where the positive or negative is equal to del dot j's value. Now we can go back and take our formulation of E equals J equals rho E. We can move, or sigma E, I'm sorry. We can take our formulation of J equals sigma E, move the sigma over to the other side, and this is our Ohm's law. And we can then take the divergence of both sides of the equation, the divergence of E and the divergence of the inverted sigma times J, and we can then take, if this is constant, we can take it out, and we get the inversion of sigma times del dot J, and for a steady current, this is 0, so del dot E is 0. And you'll remember from your first semester that del dot E is equal to the charge density. And so if del dot E equals 0, then that tells you that the charge density is 0 in a conductor. Now, that means that there is only charge buildup on the surface of the conductor. But this is something that I really want to point out because it can be a little confusing. You might think that what I'm saying here is that the current is flowing only on the surface, and that is actually not true. The current can flow through the bulk of the material. It typically does. If I have a wire and I attach it to a battery, the current is flowing through the bulk of the wire, through the full cross section of the wire. What it means to say that the net charge density is 0 is it just means that the density of positive and negative charges is the same. So if I were to take a wire, for example, and I were to look at a little piece of that wire, if I were to zoom in on just some small neighborhood around a point inside that wire, I would see charges flowing through that point. But the density of charges, of negative charges that are flowing, is equal to the density of positive charges that are staying still. Okay, so it's net neutral, but charges are flowing. And in fact, this helps provide what I would call a bottom-up explanation of what's going on with current. Imagine I have a wire and I haven't, and like there's not under any E field, I haven't done anything with it, so it's neutral. It's not only neutral, but it's boring. The negative charges are basically standing still. They're not really, but for the sake of this simplified argument, they're standing still. The positive charges are standing still, and it's net neutral. Now let's say, using a battery or an E field or something, I push a few of the electrons in the back of the wire forward, okay? That's going to suddenly change the density of negative charges. It's going to make the density of negative charges higher than the density of positive charges. There's going to be a net E field, and that's going to push the electrons that are in front of those electrons forward, and then those electrons are going to push the electrons in front of them, and everything is going to move until it equalizes, and you have the same amount of negative charges as positive charges per unit volume. And again, I repeat that the negative charges are flowing. They're flowing in a forward direction. The positive charges are stationary, but the density of negative and positive charges is the same. And this is really, if you recall from the first semester, this is just a statement of the fact that for a perfect conductor, the E field equals 0. Charges will rearrange themselves to cancel the E field. Where does charge buildup become relevant? Well, let's say that I have a wire, right? And current is going axially down that wire. You could think of, here, I'm actually going to draw this. You could think of, if it's just a straight wire, it sort of makes sense to you that the charges are going to be moving axially. But let's say that I bend the wire. What is going to sort of help keep the charges going in that axial direction? Well, wherever there are bends, you can have charge buildups that are on the surface that sort of redirect the charges. And so that's basically the phenomenology of how current flow works inside conductors. And so this statement that the field inside a perfect conductor is 0 and that there's no net charge density, that doesn't mean that the charge isn't flowing through the conductor. It simply means that there isn't a higher density of negative to positive charges in the conductor. All right, so moving on, we are now going to show that the Laplace equation holds in this case. And the way that we do that is we recall from the first semester that the relationship, and this is really definitional, between the E field and the scalar potential is that the E field is equal to the gradient of the scalar potential, V. And therefore, if I do del dot E, so if I take the divergence of the E field, that is the same as del dot del V, which is just del squared V. And since we already argued that del dot E is 0 in the case of a good conductor, then del squared V is going to be equal to 0. And this means that we satisfy the Laplace equation. This means that we can use the machinery of the Laplace equation to solve for scenarios involving wires, as long as we're dealing with a conductor that is carrying a steady current. So that's for a conductor carrying a steady current. And this is more general than a perfect conductor. So this is more general than a perfect conductor. It also applies to finite but uniform good conductors. So you don't have to have a perfect conductor. Um, it holds for finite but uniform real conductors. Okay. So that really gives us a lot of machinery that we would need to solve for the macroscopic relationship between fields and currents. Now, one of the things that comes out of Laplace's equation is the uniqueness theorem. So we have the uniqueness theorem, which tells us that the solution to Laplace's equation is uniquely determined if the electric potential is defined on the bounding surface. Essentially what it's saying is that we have this differential equation here, and if we have boundary conditions, then there's going to be one specific unique solution. Enough talking about this in the abstract, let's actually work out a problem, the problem of an arbitrary wire. So let's say that we have a material, and it can have an irregular cross section, but it has this sort of wire-like property that it is a bulk material that continues along with the same thickness everywhere to some backside. I'll just kind of draw that. And let's give the following conditions. We have at this side V equals V naught, and on this side V equals 0. So this is going to set our boundary conditions. And this is at the location z equals 0, and this is at the location z equals L. So this length here is length L. And now we can write out Laplace's equation. And we have that del squared V equals 0. And this is Laplace equation with the following boundary conditions. Okay. Boundary condition 1 is that the voltage or the potential evaluated at z equals L is equal to V naught. The second boundary condition is that v at z equals 0 is equal to 0. And there's a third boundary condition, which is the one that you may have been wondering about when I set this problem up. Oh, and by the way, we're going to say that obviously sigma is uniform, and we'll just call it sigma naught. The the third boundary condition, the one that I haven't stated, you might have been wondering, well, in order to have uniqueness, we need to define the potential at all parts of the surface, the bounding surface, and I only talked about these two sides, here and here. What about the edges? And that's where our third boundary condition comes in. Our third boundary condition is that j dot n, where n is the normal vector to the surface, is equal to 0 on the side surface. And this is really just a way of saying that charges can't escape the surface of the wire. If j dot n hat did not equal 0, it would mean that a current was flowing along this direction, which means that current would be flowing out of the wire. And definitionally, the way that we have this problem set up, that is not the case. The currents stay, the charges stay bound to the surface. Another way of writing this is that sigma E dot n is equal to 0, um, which we can write as sigma, the gradient of v dot n hat is equal to 0. And we can also write that as del v del n at the surface equals 0. And that's really a more proper way of saying this, because you'll recall that the uniqueness theorem says that we have to define specifically the electric potential at all points along the surface. And this is an expression for potential. This is an expression for potential. This technically isn't, but this is. It tells us that the gradient of the voltage in the direction normal to the wire has to be equal to 0. And again, that's sort of consistent with this point that charges cannot leave the surface. Okay, so this, hold on one second. This suffices for the uniqueness theorem as having a unique solution. And what we're going to do now is we're going to do the hand wavy physicist, I kind of know the answer ahead of time way of solving differential equations, where we're going to guess a solution. Although you should have some intuition on this. And you'll see how that intuition bears out when I actually show it executed, where we're going to say that the solution is that v of z equals v0 times z divided by L. Now, what is this basically? This is a linear equation in z, a linear equation in z. Why did we go for that? We went for it precisely because Laplace's equation is taking a second derivative, and we know that the first derivative of a linear function is going to be a constant. So if I do del v del z, I'm going to get v0L, which is a constant. And if I take the second derivative, oops, that's going to equal 0. And bam, that's our Laplace's equation. Right? And we're only doing it along the z-axis because we have already established, based on the symmetry of this problem, that all of the relevant directionality is in the z direction. We know that the gradient of the E field in the radial direction, normal to the surface of the wire, is going to be 0, that everything is going to cancel itself out. And so all of the variation that we have to worry about is, along the direction of this axis. Actually, I drew that arrow backwards. Technically speaking, let's actually draw it in. The direction of the E field in this problem would be this way. And yeah, so we now have a form for our solution that we have shown works for, it satisfies Laplace's equation. Now, the uniqueness theorem guarantees that this is the only solution. And we have, of course, the other following conditions. So again, going back, our solution is v of z is equal to v naught z over L. And we can see that v of z equals 0 is indeed 0. And we can see that v of z equals L is indeed v naught. And so this meets our boundary conditions. And again, and as I was just arguing about the symmetry of this problem, that it is purely along the z-axis, that also satisfies the third boundary condition.